This is my Precalculus course. Today we're going to learn how to graph polar equations, and we're going to convert between polar form and rectangular form. If you haven't done the homework completely and correctly from the last class, do that homework before watching this video. In the previous class, we learned how to graph polar coordinates, and we converted between coordinates in polar form and rectangular form, and vice versa. Now we're going to graph polar equations like the one you see here. A rectangular equation is an equation that has x's and y's. For example, you might see something like this. That's an equation in rectangular form. But notice in this equation we have theta and r. That means that this is an equation in polar form. And it's very important that you have your graphing calculator ready. If you don't have a graphing calculator already, you're going to need one before you do this class today. So if you don't have one, stop the video and go out and get your graphing calculator. You're going to need one at some point in your math education. Now, the reason we're going to need the graphing calculator is it's not really practical to plot every single point that we need to draw an accurate graph of this equation. So whenever we graph polar equations, we're going to need our calculator to assist us. And I'm going to show you how to use the TI-84 Plus, the most popular graphing calculator. You can find graphing calculators on the Google Play Store or the Apple App Store, but you're not really allowed to use those graphing calculators in the academic world. You're not allowed to use your phone. Also, the basic calculator on your iPhone or your Android phone, they're not going to graph what we need to graph today. And scientific calculators are not going to work either. So you really need to have a graphing calculator. If you don't want to buy a TI-84 Plus, then you can get a used one for, $20-30 bucks, but I'm not going to be able to show you how to use that calculator. You can also use Hewlett-Packard's or Casio's or whatever you want to use, but just be aware it's up to you to figure out how to graph using those calculators. But if you're using a TI-84 Plus, you want to press the mode button at the upper left, and you're going to use the down arrow key at the upper right. And notice it says radians and degrees. You're going to want to make sure that you're in degree mode. And notice below that it says function and parameter and polar. You want to make sure that you're on polar mode. So go to pole and highlight pole. So you should be in degree mode and polar. So that means that we're going to be in polar form now. So I want you to press the blue second button at the upper left, and then the mode button again, and that quits out of that screen. Now I want you to press the button at the upper left, the far upper left, that says y equals. It also says stat plot in F1. Now notice that it says R1 equals. It doesn't say Y1, it says R1, because that means we're now in polar form, or we're in polar mode. And we're going to graph this equation, so I want you to enter that equation in. You're going to enter 3, and then push the sign button, and then 2, and then at the upper left, you see how it says x, t, theta, n. There's one button that says x, t, theta, n. You're going to press that, and then you don't really have to, but you can push the right parenthesis button, and you should see this exact equation in your calculator. So at that point, I want you to push the upper right button, the button at the highest button at the right that says graph. It says table F5, it says graph. Press that, and you should see something on your screen. Now, if you don't see something on your screen, that's okay. We have to learn how to adjust the window. So I want you to push the window button at the upper left, right next to the Y equals button. And your calculator is probably going to say theta minimum negative 180 degrees and theta maximum positive 180 degrees. And it should say theta step equals 1. That means that your graph is plotting points at theta intervals of 1 degree. So it'll plot, for example, 0 degrees, then 1 degree, then 2 degree, then 3 degree, then 4 degrees, so on and so forth. If you make the steps smaller, it'll take longer for the calculator to graph the plot, but it'll be more accurate. But you just want to keep it at theta step 1, and theta minimum negative 180 to positive 180, that's probably going to be best for us. That just means that those are all the theta values that the graph is going to plot. So for x minimum, I want you to enter negative 3, and for x maximum, I want you to enter positive 3. And x scale, that's what that stands for. X SCL is the x scale. That just tells you how many units on the horizontal axis each tick mark is going to be. For y minimum, I want you to enter negative 3, and for y max, positive 3. And y scale, again, is probably going to be 1. Just keep it at 1. So x max and min are just the horizontal max and min window. That tells you your window. And y max and min are the vertical. So now I want you to press the graph button at the upper right, where it says table F5. Push the graph button. And now you should have what looks like a 4-leaf clover. Now, if for some reason you don't see it, then you need to adjust the window. And it takes a while to get used to how to do this, so don't get frustrated. If you're only seeing part of the graph, then that means you need to change your theta minimum and theta maximum values. If you don't have enough theta values, or if your theta range is not big enough, then your calculator is only going to graph part of it, part of the picture. So it's very common to have problems with the calculator. So if you do have problems, don't panic. You just have to adjust something in your window. So push the window button and just play with the numbers until you get the right graph. So we're going to graph this, but the calculator is only going to be an aid. It's going to assist us. But you need to demonstrate that you can actually plot some of these points yourself. So you're not going to get away with just trying to draw the graph with your calculator. That's not going to be enough. We do have to plot some points, and that's why I'm instructing you to write the coordinates of at least 4 points. So we could trace on the graph, but those values are not going to be necessarily easy numbers to deal with. So we're going to do some of the math ourselves. So I like to choose theta is equal to 0. We can choose any theta value that we want, but 0 degrees is usually pretty easy when it comes to the math. So now we're going to calculate the R value when theta is 0 degrees. So 2 times 0 degrees is 0. So now we have sine 0 degrees. And what is sine 0 degrees? Well, that's a collapsed triangle. So remember, in trigonometry, we learned that if you have 0 degrees, we have a collapsed triangle, and you have to use the sine graph whenever you have a collapsed triangle. And collapsed triangles result when you have quadrantal angles, 0, 90, 180, 270, 360. this graph is particularly useful when you have those quadrantal angles. If you had 30 degrees or 45 or 60 or 210 or 225, then we couldn't really use this graph to help us find the values. But we know that if the if the angle is 0 degrees, then the y value on this graph is 0. So that tells us that sine 0 degrees is 0. So this is all review of things that we've done before. So now we see that if the angle is 0 degrees, then the r value is 0. So we have 0, 0 degrees. So that's just going to be at the origin. Whenever r is 0, our plot is just going to be right at the origin there. Or our point is going to be right at the origin. Okay, so now let's choose another value. I'm going to choose 45 degrees. And we're looking for values that make things easy for us to calculate. I know that if I multiply 45 by 2, I'm going to get 90 degrees, so that's why I chose that. If you choose a value that makes things difficult, that's okay. But just be aware that it might take you a little longer to graph, and you might have to use some special triangles, which we're going to do today. But we're going to try to avoid having to use these. We're going to try to employ quadrantal angles in our trig functions, so we don't have to worry about the special triangles. It just makes things easier. 2 times 45 degrees is 90 degrees. And sine 90, that's a collapsed triangle. So remember, we count out 90 degrees to the right, and we see that the value we're looking for is 1. Again, we need to use those graphs to help us with collapsed triangles. So r is equal to 3. The point is 3, comma 45 degrees. And these points are part of our answers, so we need to rectangle those. So remember, in the previous class, we learned how to plot these points. So we're going to count 3 units to the right, and then we're going to rotate 45 degrees. So that's going to get us up to about there. It doesn't have to be perfect, but it's going to be somewhere around there. So that's 2 points. Now let's find 2 more, and we can use our calculator to help us graph this, and then we'll be done. So what theta value should we choose now? I think I'm going to try negative 45 degrees, possibly. We'll see if that works. If it doesn't work, we may have to use something else. Sometimes you'll choose a theta value and it'll actually end up putting you at the same point that you already graphed. Don't worry about that. That's okay. R is equal to 3 times sine 2 times negative 45 degrees. So we have 3 times sine negative 90 degrees. And how do we calculate sine negative 90? That's a collapsed triangle. So we have to go up here and go to the left negative 90 degrees, and we see the value of sine negative 90 is negative 1. So r is equal to 3 times negative 1. So r is negative 3, and the point is negative 3, comma, negative 45 degrees. So we'll see if this works. So we're going to count out negative 3 on the x-axis because r is negative 3. Then we're going to rotate negative 45 degrees, which would actually be clockwise. So we're going to end up somewhere up here, roughly. Let's move that up a little bit. Should be symmetric about the y-axis in this case. Okay, so Let's choose one more point. What should we choose for theta? Now again, we want to stay away from 30 or 60. We could choose 180, but at this point we may want to use a special triangle just so you can remember how to calculate those values, because sometimes we're going to have to do that. So maybe we should try 105 degrees, because I know when I multiply 105 by 2, we're going to get a special angle, 210 degrees. You don't really have to find points down here. We have our graphing calculator to help us. But I just want to demonstrate how to find some of the points in the third and fourth quadrants. So we're going to plug in 105 for theta, 105 degrees, and then we get 3 times sine 210 degrees, and this is where we need to go to our special triangles. So you want to get a picture of these triangles if you need to. You should be pretty familiar with that information there. But we're going to rotate 210 degrees, which would get us here, and we need to calculate the reference angle, which would be 30 degrees. That's this this purple angle here. So we had to rotate 180 degrees. Whoops. We had to rotate 180 degrees to get to here, but then we had to rotate another purple 30 to get to 210. So again, that's all review things that you should know. So now we see that this is a special triangle, and this side is going to be omega, this side is going to be 2 omega, and this side is omega root 3. Sine is the opposite side of the triangle divided by the hypotenuse. So omega over 2 omega is 1/2. So we have 3 times 1/2. And that's going to be negative 1 over 2, because the opposite side over here, it's below the x-axis, so that's going to be negative. So now we have r is equal to negative 3/2, and our point that we're looking for is negative 3/2, comma 105 degrees. So we're going to count out negative 3/2 on the x-axis, and then we're going to rotate 105 degrees counterclockwise, which would get us to about there. So again, your graph is not going to be perfect, but we're just getting an idea of how to graph polar equations here. So now we can use our calculator. So I want you to push the on button on your calculator if it turned off, and I want you to use that as a guide to help us graph. Again, your graph is not going to be perfect, but it should look something like a 4-leaf clover. As you can see, my graph is not perfect. Maybe I can redo those bottom parts, but try your best. This is not an art class, so it doesn't have to be perfect. Don't slave over drawing the perfect graph. That's a waste of time. This is a math class, not an art class. But your graph should look something like that. So if you got that graph, good job. Let's try another one of these. We have 4 points, and we have the graph. So again, the graph doesn't look perfect, but that's okay. It doesn't have to look perfect. We're just learning the basic idea. So now let's go to our graphing calculator and push the y equals button. And I want you to push the clear button at the upper right. That's going to clear the equation. So we're now going to enter 1 minus 2 times cosine, and then push the x comma t comma theta comma n button. It's right under the mode button at the upper left, the X, comma, T, comma, theta, comma, N button, and then you can enter a right parenthesis if you want to, but you don't really need to. Then, once you have this equation in your calculator, again, push the window button to get that, or excuse me, push the Y equals button to get that at the upper left. Then push the graph button at the upper right. Again, it's the button at the upper right that says graph. And your calculator should be graphing that shape. And so now let's find 4 points to help us. We have an idea of what the graph looks like. I'm going to try theta equals 0 degrees. Again, the graph along with our points is going to help us to understand how to graph polar equations. So you need to use your graphing calculator, and you need to find these 4 points on your own. Both those two things are required. It's not an option. So we can learn how to do this. So let's plug in 0. I like choosing 0 because it's an easy value to calculate in trigonometric functions. Now cosine 0 degrees, how do we calculate that? Well, it's a collapsed triangle. So we need to go to our curve. 0 degrees tells us that the value of cosine is going to be 1. So cosine 0 degrees is 1. And r is -1. So the point is -1, comma, 0 degrees. So we're going to count out 1 to the left because it's negative, but we're not going to rotate at all. So that's the point. And now let's find a second point. Let's choose 0. I want to try to stick with quadrantal angles because they're just easier to calculate with trigonometric functions as long as we have these graphs in our minds. So we're going to plug in 90 degrees. So we have cosine 90 degrees, and how do we know what cosine 90 degrees is? Again, we go to our graph. So count out 90 degrees, and we see, whoops, that's the wrong graph. Count out 90 degrees, and we see that the value of cosine 90 is 0. So r is equal to 1. So the point that we're looking for is 1, comma, 90 degrees. So now we're going to count out 1 unit to the right, and then we're going to rotate up. So 1 to the right, and then rotate up, and then we're going to get to there. So that's another point. So now all we have to do is graph 2 more points, and then draw the graph, and we'll be done. So let's try 180 degrees. Again, if you try something and it doesn't work, or it plots the same point that you already plotted, that's okay. Don't get frustrated with this stuff. Just try some different things. Now, what is cosine 180 degrees? Well, we go to our graph because it's a collapsed triangle when you have quadrantal angles, and we see that cosine 180 is -1. So we have -1 for cosine 180. So r is equal to 1 plus 2, which is 3. And so the point we're looking for is 3, comma, 180 degrees. Okay, so let's plot that point. We're going to count out 1, 2, 3, and then we're going to rotate 180 degrees, and that gets us to there. So 3 comma 180 degrees is this point here. Okay, so let's plot one more point. Again, this is helping us to understand how to graph polar equations. I'm not going to make you draw 30 points or plot 30 points and do all the math, because that would be a waste of time. That's just too much work. But I am going to make you calculate 4 points, at least 4 points, and use your calculator to assist you. Okay, so what else should we try? Maybe we can try negative 90. Let's try that, negative 90. Again, sometimes it will just give you the same point that you already graphed, so if that happens, don't panic, just try something else. So we have 1 minus 2 times cosine 90. Cosine negative 90 is 0 if you look at the graph. Again, you should have these graphs right in front of you. If you don't have these memorized, then it's going to be very difficult. Negative 90 is 0. You can take a picture of those with your phone if you need to. So our point is 1 comma negative 90 degrees. So we're going to count out 1 on the x-axis, and then we're going to rotate negative 90, so we're going to go all the way to here. That's clockwise. So now we have 4 points. Now we're going to go to our graphing calculator, and the graphing calculator is going to help us see the basic form of the graph. So it looks like our graph is going to go, it's not going to go past y equals negative 2. Looks like it's going to go maybe about halfway between y equals negative 1 and y equals negative 2. Again, your graph doesn't have to be perfect. Now, you're going to find that the graph does go through the origin. We didn't find a point, but it does go through the origin. So that's not perfect, but it doesn't have to be perfect. I know that there's a lot of artists out there that are going to be drawing these graphs, and you're going to think, I have to make this perfect. Don't waste your time. Are you listening to me? Don't waste your time trying to make a perfect graph. This is not an art class. All right. Let's rectangle these points here. If you got that graph, excellent. So again, most important thing to understand is we're plotting 4 points using the equation, but we're also using our graphing calculator to assist us. So let's do one more of these before you try one on your own by yourself. So I'm going to try 0 degrees for theta as usual. And sine 0 degrees is 0 if you look at your your graph, because your sine graph, because it's a collapsed triangle. So r is 2, so the point that we just found is 2 comma 0. So we're going to count out 2 units on the x-axis, and we're not going to rotate at all, so our point is just going to be there. Okay, so now let's try, I don't know, what else should we try? Maybe we can try 90 degrees. So let's plug that in, and we get 2 plus sine 90 in the denominator. If you go to your sine graph, you'll know that sine 90 is 1. So r is equal to 4/3. So the point that we're looking for is 4/3, comma, 90 degrees. So we're going to count out 4/3 to the right and then rotate 90 degrees. So that's going to get us to about there. So now we have 2 points. All we have to do is find 2 more points, and then we can graph this. And I haven't entered the equation into my calculator yet, so we'll do that later. Let's try, maybe we can try -90. Again, you want to stick with quadrantal angles if you can. 0, 90, 180, 270, so on and so forth. So r is equal to 4 over 2 plus sine -90 degrees. So if you look at your sine curve, sine -90 is equal to -1. So then we're left with 4. R is equal to 4. So the point that we're looking for is 4 comma -90 degrees. So we're going to count out 1, 2, 3, 4, which is actually off the scale, but that's okay because when we rotate down, we're still on the scale, so that's going to be that point there. Or we're still on the window, I mean. Not the scale, the window. So again, -90 means you rotate clockwise. So now we just have to find one more point, and then we'll be ready to graph this. I think I'm going to choose 180 degrees. We'll see if that works. So r is equal to 4 over 2 plus sine 180 degrees. So we have 4 over 2 plus 0, because sine 180 is 0. You can see that on your sine curve. So the point that we're looking for is 2 comma 180 degrees. Let's plot that. We're going to count out 2 units to the right and then rotate 180 degrees, and that's going to get us to there. So this is not enough information to help us graph this. So we need to go to the calculator. I want you to press the y equals button at the upper left. Y equals button at the upper left. Push the clear button at the upper right. Then I want you to press the green alpha button. Now you don't have to use the alpha button, but it's going to be a lot easier for you. The green alpha button is at the upper left. It's possible that some of you are using different colored calculators, so it might not be green if you're using a TI. Push the alpha button, and then I want you to push the y equals button at the upper left. Now you see how it says n/d for number 1. I want you to push enter. And now you see we have a very convenient fraction template. That's one of the most powerful tools that you're going to use in a graphing calculator. If you know how to do that, it'll tremendously increase your competency when it comes to using a graphing calculator. Because the biggest problem with these calculators is not entering the expressions or equations properly. So now you're going to enter 4 and then the down arrow key at the upper right, and then 2 plus sine, and then the x comma t comma theta comma n button right under the mode button. And so you should have that expression in your calculator. Press graph, and it looks like this graph is not going to fit on our window. That's okay. So it's very common for graphs not to fit on the window. So what do? Well, we just push the window button at the upper left. Table set F2 window button. And now I'm going to go down and I'm going to change Y minimum to -5. And I'm going to push the graph button again. So you want to change Y minimum to -5 and then push graph again. So now you should have something that looks like an ellipse, and actually it is an ellipse. This is the polar form of an equation of an ellipse. So that gives us an idea of what the ellipse looks like. So it looks like it goes all the way out to maybe around here, are the farthest points that it goes out. And so let's connect the dots. Now, notice that this doesn't look like the graph on your calculator. That's because the spacing for the horizontal axis is different from the spacing for each tick mark on the vertical axis. So it looks somewhat different. I know that's kind of annoying, but our squares on this graph, as you can see, have equal spacing. So this is what it's going to look like in that situation. So if your graph doesn't look exactly the same, that's okay. So again, the spacing for the tick marks on the horizontal axis on your graph might be different from the spacing of the tick marks on the vertical axis. That's why the graph looks different. On a calculator, your graph looks something more like this. Okay, so I want you to get a screenshot of all this information here. Get a picture of these with your phone, or take a screenshot, get a picture of these, and I want you to get a picture of these first two problems that we did. And you can use number 3 to help you. Try number 4. Now, the first thing you need to do is enter this equation into your calculator. So I want you to go ahead and do that now. So press the Y equals button at the upper left, and press clear at the upper right, the clear button, and then cosine 3, and then the x comma t comma theta button, and then end parenthesis, right parenthesis, and then push the graph button. Now when you graph this, notice that the shape is kind of small. So what does that mean? It just means that we have to change the window a little bit. So once that's done graphing, I want you to press the window button and go to X minimum and enter -1, and we'll try +1 for the X max. So your X minimum should be -1, your X max should be +1. And this window that I drew for you should be kind of a clue as to how to, determine your window. So the Y minimum should be -2, the Y max should be 2, and then push the graph button, and that should give you a better window. So again, don't get frustrated with your calculator. It's very easy to make mistakes. You just have to play with your calculator and make sure that you figure out how to do this just by trial and error if you have any problems. And remember, you can go on the internet, YouTube or Google or wherever you want to go, to find information about how to use your calculator. Just plug in, if you're using a Hewlett-Packard or a Casio or a TI or whatever, just plug in or type the name of the calculator, and there's it's a good chance that somebody's going to give you some clues as to how to use it. So now that you have the graph in your calculator, it should look something like this, something like that. Now I want you to find 4 points using this equation and go ahead and graph it. And when you come back, we'll do it together. Okay, we're back. So I'm going to choose 0 degrees. I always choose 0 because that seems like an easy number to choose. In most cases, it's a pretty easy number. So cosine 0 degrees is 1. So our point is 1 comma 0 degrees. So I'm going to count out 1 to the right, and I'm not going to rotate it at all, so I have that point there. So now I'm going to choose another theta value, and it's a little bit more difficult to find theta values that are going to help us here because we're multiplying theta by 3, so I'm sorry about that, but that's just a difficulty of this particular problem. We could try maybe 90 degrees. I don't know if that's going to work, but we can try it. So r is equal to cosine 3 times 90 degrees, and that is cosine 270 degrees. So if you look at your cosine graph, 270 degrees is going to give us 0. So that does look like a different point. So when the r value is 0, then the point is always going to be right on the origin. So we have that point there. Now we just have to find 2 more points. So what should we choose now? We want to produce a quadrantal angle if we can. If we choose 30 degrees, that will give us a quadrantal angle, but that will just give us 0. Cosine 90 is 0, so that's not really going to do anything for us. If the r value is 0, we're just going to get the same point at the origin. So let's see, what else can we do here? How about 60 degrees? So let's try 60 degrees. R is equal to cosine 3 times 60 degrees. The reason I chose 60 is because I know if I multiply that by 3, we get 180 degrees, and that's a quadrantal angle. So if you look at your cosine curve, cosine 180 is actually -1. So our point is -1, 60 degrees. So that's definitely a different point. You have to choose 4 different points. So we're going to count out -1 and then rotate 60 degrees in the counterclockwise direction, and that will get us to about there. Again, your points don't have to be perfect. Okay, now what should we do? Maybe -60 will work. I'm going to try it. R is equal to cosine 3 times -60. So cosine -180 degrees. We must use parentheses when you're writing a negative angle inside a trigonometric function. So cosine -180 is also -1, but it's a different angle. It's not positive 60 degrees, it's negative 60 degrees. Okay, so -1, negative 60 degrees. That's going to get us about here. roughly. Should be exactly on top of that other point. Okay, so now we can go to our calculators, and you can use the, it looks like these points go about halfway to the -1 mark, so it looks like we're accurate on that. So if your calculator turns off, you can just push the on button. So we're going to write this leaf here, and again, it doesn't have to be a completely accurate graph, just a rough estimate of what the graph is going to look like. Now again, your graphing calculator may look different because that's the horizontal axis has a different length for the tick marks, and the vertical axis has a different length. So I'm not sure why the calculator does that. You might be able to adjust the window on that. So on further inspection, it seems like the graph doesn't go quite so far out to the left. If you look at your graph closely, apparently it's going to do something more like this. So just get as accurate as you can. Again, it doesn't have to be perfect. Alright, so if you got that answer, something that looks like that, good job. Okay, I want you to attempt number 5. You can take a picture of these two problems if you want to. And if you haven't gotten a picture of these problems, go ahead and do that. Try number 5. I want you to enter this equation in your calculator first, so press the window button. Press clear at the upper right. 3 plus sine theta, right parenthesis. And again, the theta button is the xt theta n button under the mode button. And then press graph. And you may have to change the window in your calculator, so don't be afraid to do that. In fact, you're definitely going to have to change the window button, because in the previous problem, our window was pretty small. So wait for the graph to finish graphing and then press the window button. And again, this graph here gives you a clue as to what you're going to need. So our x maximum is going to be, looks like 4, and our x minimum is going to be -4, and our y minimum is going to be -2, and our y max is going to be 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. So now push the graph button, and your graph should be it should be on the window. Alright, so there you go. So go ahead and graph number 5. Remember, you want to find 4 points. When you come back, we'll do it together. Okay, we're back. I'm going to start with theta is equal to 0 degrees. So sine 0 degrees is 0, as I'm sure many of you remember. You don't have to show all of this math. You can do the math by skipping a lot of steps here. So 3, 0 degrees is 1 point. We're going to count out 3 to the right. 1, 2, 3. And we're going to rotate 0 degrees. So now let's try theta is equal to 90 degrees. Again, we want to stick with quadrantal angles in our sine function. And of course, I'm talking about quadrantal angles that result after we do the math in the trig function. In this case, there is no math in the actual trig function. It's just plugging in theta. But if we had 2 theta or 3 theta, it would be a different situation. So we have 3 plus 2 times sine 90 degrees. And sine 90 is 1. You can see that by looking on your sine curve. And so r is equal to 5, so the point that we're looking for is 5 comma 90 degrees. So I'm going to count out 1, 2, 3, 4, 5, and we're off the window. But that's okay because we're going to rotate 90 degrees all the way up to here. Whoops, I got rid of my other point there. Let me bring that back. Computer's going kind of slow. Alright, so we have the point there. And let's choose another theta value. We have 2 more points and then we can graph it and we'll be done. So maybe we can try negative 90 degrees. So r is equal to 3 plus 2 times sine negative 90. Sine negative 90 would be negative 1. So I have 3 minus 2. We have 1. So r, so we have 1 comma negative 90 degrees. There you go. So we're going to count out 1 unit. 1 unit to the right. And then rotate negative 90, so clockwise, so we get to this point here. Okay, now we have 3 points, we just need 1 more. Let's see, we could choose maybe 30 degrees. I'm going to choose 30 just so we can get some practice with our special angles. So if theta is 30 degrees, we're going to calculate r. So sine 30 degrees is 1/2. How do I know that? Well, we have to use our special triangles. Our 30, 60, 90 degree triangle specifically. And what this means is that we're going to rotate 30 degrees and we have a 30, 60, 90 triangle. This side is always omega root 3, this side is omega, and this side is 2 omega. In this case, we're in the first quadrant, so all sides will be positive. And sine is the opposite side over the hypotenuse, so that's going to be positive 1/2. So r is equal to 3 plus 1, which is 4. 4 comma 30 degrees is our point. So we're going to count out 4 units. 1, 2, 3, 4, and then rotate 30 degrees, which would get us to about there. Roughly. It doesn't have to be perfectly plotted. Okay, so now we can go to the calculator. We have a pretty good idea of what it looks like. So, looks like it's going to be something like this. We see we have symmetry. So we can plot that point and this point and use those points to help us, again, using symmetry. And it kind of looks like an upside down heart. Okay, so again, it may not look exactly the same as your graphing calculator because our squares are they're equidistant, or the squares are the same size. They're not rectangles, they're squares on our graph, but on your graphing calculator you see the vertical tick marks don't have the same spacing as the horizontal tick marks, so that's why it looks somewhat different. Okay, so if you got that right, excellent. Go ahead and try number 6. Now I'm going to warn you that number 6 is, well, you'll see what it is when you enter it into your calculator. So press the y equals button and the clear button at the upper right. Now this is a fraction, so how do you deal with fractions? Well, you push the green alpha button, which is under this blue second button at the upper left. Alpha. Then I want you to push the y equals button at the upper left. So you push the alpha green button, and then you push the y equals button at the upper left. You should see a list, 1, 2, 3, 4. Press on number 1 that says n/d. So then you're going to enter 4 and then the down arrow key to get to the denominator, and then 2 minus 3 cosine, and then the x comma t comma theta comma n button, and then a right parenthesis if you want to do that. I don't think you need to, but then we're going to press graph. Now the graph may not be in the window. It might be out of the window. That's okay. And you should be aware that your graph is going to include asymptotes. If you're using a TI 84 plus, the graph is actually going to plot the asymptotes. This is actually a hyperbola. So now we're going to change the scale. Press the window button, and this picture here is going to show you which window that you want. So we want the minimum x value to be -6, it looks like. Minimum x should be -6. The maximum x should be 3. Minimum y should be -4. And maximum y should be 1, 2, 3, 4, 5, it looks like. Then press graph. So now we'll get a better understanding of what this hyperbola looks like. So I'll go ahead and allow that to graph, and you should have a pretty good picture there. Now again, those straight lines are not part of the graph. Those are just asymptotes that show you how to graph it. So I want you to try number 6. Find 4 points using the equation. Try to stick with quadrantal angles, but if you can't find quadrantal angles, then you can plug in 30 or 45 or 60 or -30 or -45 or -60 and use your special triangles. So try number 6. When you come back, we'll do it together. Okay, we're back. So I'm going to try 0 degrees for theta. I always choose 0 first. So cosine 0 degrees is equal to 1. So we have 4 over 2 minus 3 times 1, which is -4. So the point that we're looking for is -4 comma 0 degrees. So I'm going to count out -4, which means I have to go to the left, and then I'm going to rotate 0 degrees, which means I'm not going to rotate at all. So that's the point there. And now let's try plotting 90 degrees. So r is equal to 4 over 2 minus 3 times cosine 90 degrees. Sorry that we're off the page there. Now if you look at your cosine curve, you see that cosine 90 is actually going to be 0. So that's 4 over 2 minus 3 times 0, which means that r is 2, and the point we're looking for is 2 comma 90 degrees. So we're going to count 2 units to the right and then rotate 90 degrees, and we get that point there. So now all we have to do is find 2 more points. Let's try maybe we can try negative 90. We'll see if that works. The only reason it wouldn't work is because it might give us the same point that we already graphed. So if you look at your cosine graph, cosine negative 90 is 0. So we have 3 times 0. So r is equal to 2. And the point that we're looking for is 2 comma negative 90 degrees. So we're going to count 2 to the right and then rotate negative 90, which gets us to there. So that was actually a pretty good point there. That really helps us to graph it. So now, what should we choose for theta? I'm going to choose 180 degrees. I don't know if that's going to be the best point, but all we have to do is find 3 distinct points on the graph. So cosine 180 degrees is negative 1. So we have 4 over 2 plus 3, which is 4/5. Let me make some more room. So if r is equal to 4/5, our point that we're looking for is 4/5, comma 180 degrees. Sorry, my computer's going kind of slow here. Okay, 4/5, 180 degrees is going to get us to about here, because we go out 4/5 and we rotate 180 degrees to get to there. Okay, so if your calculator turned off, press the on button. And we see that the asymptotes seem to be crossing somewhere around here. And so our hyperbola is going to look something like this. Now again, your hyperbola doesn't have to be perfect, and you don't really have to graph the asymptotes. I'm not going to make you do that. But you can see that the x-intercept is where the vertex is, so that's useful to see that. That's at negative 4. So if you got something like that, good. Now again, you don't have to graph the green asymptotes. If you graph the asymptotes, that's fine, but you don't have to. So that's the basic idea of how to graph polar equations. Now we're just going to do some special examples. So here's a very simple polar equation. R is equal to 2. So what does that look like? Well, remember we have equations in rectangular form like x equals 2 or y equals negative 1. In this equation, y is not there, and in this equation, x is not there. So it's kind of weird. We interpret this to mean that the x value is always equal to 2, and the y values can be anything. So what that means is it's going to be a vertical line at x equals 2. This means that the y values have to be negative 1, but the x values can be anything. So that means it's a horizontal line at y equals negative 1. Now, when you're in polar form, and it tells you that r is equal to 2, but theta is not even in the equation, what that means is that your angle can be anything, but your r value has to be 2. R cannot change. So think about that. If you go out 2 units to the right and your theta value can be anything, but your R value always has to stay the same, well, what are you going to create? Look at all these points at the end. What are you creating? Well, it's just a circle. My circle didn't look perfect, but that's the graph. It's actually a circle. Now, if you forget this, I want you to be able to convert this equation to rectangular form so that you can always remember that that is just the equation of a circle. Remember that if we plot a point using x and y values, that red point there, and then we try to come up with a picture showing us the relation between a point in rectangular form and polar form, we see that r is just the hypotenuse of the corresponding right triangle created by the x and y values. X and y are the legs of the right triangle, and theta is just the acute angle. Well, it doesn't have to be acute, but in this case it's the acute angle. It's the angle in standard position inside that right triangle. So what that means is we can use the Pythagorean theorem to give us a relation between x, y, and r. So what I can do is write that equation down here, and I can actually just square both sides of the equation. Then we get r squared is equal to 2 squared, and we get r squared is equal to 4. So if you graph this equation, you get the same thing that you would get if you graph this equation, because all we did is just square both sides. You can do anything to both sides of an equation and it doesn't change the equation. There are some situations where if you multiply both sides of an equation by 0, that would definitely change the form. And sometimes you have to worry about signs and various things, but in this case it's not really going to hurt us to square both sides of the equation. And we see up here that r squared is equal to x squared plus y squared. So we're going to substitute x squared plus y squared for r squared. And this should be somewhat familiar to you. That's the equation of a circle. You can put it in standard form, or think of it as standard form if you write x minus 0. And remember, r squared is equal to 4. So we see the radius is 2, and the center of the circle is 0, 0. So you don't have to do that math. You just have to remember that r equals 2 is the equation of a circle. So now we draw the circle, and we're done. Okay, so here's another example. R equals 3. Well, what's that going to look like? Well, it's just a circle centered at the origin with radius 3. Now we could translate the circles, but the math would get a little bit weird. So we're going to stay away from those graphs. All you need to do is learn the basic idea of how to graph these polar equations. We're not going to make things purposely confusing. So see if you can graph number 9. When you come back, we'll do it together. Okay, we're back. So the radius is 4. Connect the dots, and we're done. Your graph doesn't have to look perfect. If you got that right, good job. Try number 10. When you come back, we'll do it together. Okay, we're back. So the radius of the circle is 1, and there you go. So not too difficult to graph those. Let's try another special problem. So remember, we use this picture to help us convert between rectangular coordinates and polar coordinates, and we can do the same when it comes to rectangular equations and polar equations. We use this picture. Recall in the previous class that we came up with these relations because we know basic trigonometry. We know that cosine theta is defined to be the adjacent side of the triangle divided by the hypotenuse. So the adjacent side divided by the hypotenuse. And we come up with this equation down here. If we solve for x, we can see that x is always going to be equal to r times cosine theta, and the same thing with y. Y is equal to r times another trigonometric function, cosine theta. So there's a lot of different ways to think about this, but what I'm going to do is I'm going to rewrite this equation down here. There isn't just one way to do this, but I'm going to multiply both sides of the equation by r. So just to make it clear what I did there, I'm going to show that work. You don't have to show that because that's just a basic equation, obviously, or basic operation. But we multiplied both sides by r. And the reason I did that is because now we know that x is equal to r times cosine theta. So I can just replace r times cosine theta with x, and now we have the equation that we're looking for, but it's more familiar to us. It's in rectangular form. So what is that? Well, that's just a straight line. It's a vertical line. Okay, x equals 4 is just a vertical line. So believe it or not, this equation is just a vertical line at x equals 4. So if you plug in some theta value, 90 degrees actually it wouldn't work. If you plug in maybe 30 degrees, then it'll give you an r value that will take you right to there. If you plug in 60 degrees, it'll give you an r value that'll take you up to here, and so on and so forth. Again, that it's hard to believe, but that's actually just a vertical line. So now we have an even easier situation with this graph, because r sine theta we know is just y. So we can just rewrite that equation just to show the work and just plug in y for r sine theta. So now we know that this is just a horizontal line at y equals -1. So there you go. So these are just special examples where we're converting polar equations to rectangular equations. So I want you to get a picture of these problems here and all that math, and I want you to try number 13. When you come back, we'll do it together. Alright, we're back. So I'm going to multiply both sides by r. You don't have to do it this way, but this is just the easiest way to see what we're doing. R times sine theta is equal to y. So now we see what the equation really is. It's just a horizontal line at y equals 3. Alright, so if you got that one right, perfect. Try number 14. When you come back, we'll do it together. Okay, we're back. So r times cosine theta is just x. Again, based on the definition of r and theta and x, we can just turn r cosine theta into x. So now we have a vertical line at x equals 2. So again, these are just very easy examples of how to convert from polar form of an equation to rectangular form. Now this is a polar equation too, because we have theta, but in this case r is not there. Okay, so we had a type of problem where we had r is equal to some number, but theta was not there. Well, now theta is in the equation, but r is not. So what that means is that r can really be anything. It can be any number. Now let's think about this. Theta has to be 120. So you're going to rotate up 120, which is going to get us to about there. But r can be anything. So you can go out this much and rotate. You can go out this much and rotate. You can go a shorter distance and rotate. But because theta is always 120, what are you going to get? Well, you're going to get a straight line. So theta equals 120 is actually a straight line. Now to demonstrate that, we're going to use, again, our picture here. It's all based on this simple trigonometry. Well, maybe we shouldn't call it simple, but it's this basic trig that we learned in the previous class. Based on our definition of the tangent theta function, we know tangent theta is equal to the side opposite over the side adjacent in that triangle, which is y over x. So we know tangent theta is equal to y over x, but if theta is always equal to 120, we can just plug in 120 for theta. That's the one thing that we do know, that tangent, that theta is 120 degrees. So now, if we rotate 120, the reference angle is going to be 60 degrees. And we're using our special triangle here, 30, 60, 90 triangle. And by the way, we haven't used a 45, 45, 90 degree triangle yet today. We just haven't done that. Now, this side is going to be negative, obviously, right? So tangent is going to be the opposite side over the adjacent, which is negative root 3. And I'm going to keep this on the screen so you can refer to that. Sorry, my computer's going kind of slow. So negative root 3 is tangent 120. So then I'm going to multiply both sides by x. And that is what the equation looks like. So you can see that it's just a straight line. And the slope is negative root 3. So that's going to look something like this. Your line doesn't have to be perfect. So you want to go to the calculator. Root 3 is 1.73, so you're going to go down 1.73 and to the right 1, or up 1.73 and to the left 1. Okay, so again, these are examples where converting to rectangular form helps us to graph. You don't have to convert to rectangular form, but it just helps us to see what's going on. So now, again, we know that tangent theta is equal to y over x. In this problem, it tells us that theta, but 220 degrees is not a special angle, so now we have to actually go to the calculator. So on the calculator, press tangent and then 220 and then enter, and we get 0.839. So it's roughly 0.839 is equal to y over x, multiply both sides by x, and maybe we should say approximately equal to, just to be accurate. You don't really have to write approximately equal to, but so now we're going to go to the right 1 and up 0.83, to the right 1 and up 0.83, so on and so forth. And then we can connect the dots. So that's a line going up from left to right. So I want you to take a picture of these two problems, and I want you to do number 17. When you come back, we'll do it together. Okay, we're back. So tangent theta is equal to y over x. Theta is equal to negative 45 degrees. So now we have to use, we're going to rotate down negative 45. We're going to have to use a 45, 45, 45, 45, 90 degree triangle. And this side is omega, this side is negative omega, and this side is omega root 2. So tangent negative 45 is opposite over adjacent, which gives us negative 1. And I should probably keep that and just put it down here. So that's equal to negative 1. Multiply both sides by x, and we get negative x is equal to 1. So that's very easy to graph. That's just going to look like this. Okay. So if you got that right, good job. Now for number 18, you're going to need the calculator, because we cannot compute tangent 10 degrees very easily. So use the calculator for tangent 10 degrees. When you come back, we'll do it together. Alright, we're back. So we know tangent theta is equal to y over x based on our definitions for the theta values and y and x values. Theta is always going to be 10 degrees, so we can just plug that in there. And using our calculator, tangent 10 degrees is about 0.167 approximately. Multiply both sides by x. And so that's what the equation looks like. It's just a line in slope-intercept form. So we're going to go to the right 1 and up 0.16, and again, and our graph should look something like that. Doesn't have to be perfect. So if you got that right, good. Okay, so now we're going to switch to something different here. Notice that in the previous 5, 6, 7 problems, we converted from a polar equation to a rectangular equation to help us graph. So we did that over here. We converted r equals 2 to x squared plus y squared equals 4. So we converted from polar form to rectangular form. And we did that here too. We had cosine theta is equal to 4 over r, and we converted to x equals 4. X equals 4 is the same thing as cosine theta equals 4 over r. So we converted from polar form to rectangular form. And we did the same thing here. We had theta is equal to 120, that's polar form, and we converted to negative x root 3 is equal to y, that's rectangular form. Now we're going to do that a little more. We're not going to graph, but we're just going to convert equations in polar form to the corresponding rectangular form. And we're going to use these tools to help us along with this graph. So get a picture with your phone or take a screenshot. You're going to need these equations as we work along with each other in these problems. We're starting out with an easy one. This equation is in polar form because we have an r. We want to convert so that there's only x and y variables rather than the r variable. Notice up here r squared is x squared plus y squared, so we can just replace r squared with x squared plus y squared, and we're done. So we converted from polar form to rectangular form. And we can see that this is a circle with radius 3. So again, we're going to be converting equations from polar form to rectangular form. Now, this is an equation in polar form because we have r's and thetas. We want to convert so that the variables are x's and y's. Again, we have r's and thetas. We want to convert the equation so that we only have x's and y's. Now, notice we have an r here instead of an r squared. We know that x squared plus y squared is equal to r squared. That comes from this equation over here. And so r would be equal to the square root of x squared plus y squared. Now, in my trigonometry course, we allowed r to be positive only. By definition, r was never a negative value. But notice in this class, in the previous class, we've actually allowed r to be negative when we're graphing polar equations, so we're breaking the rules. Mathematicians sometimes do that. For example, imaginary numbers. You're not supposed to square a number and get a negative, but with imaginary numbers, we break the rules. So r can be negative, and so when you square root both sides of the equation, technically we need to write a plus or minus symbol. So that presents potential problems when it comes to writing the equations and analyzing them. When we convert from the polar form of an equation to the rectangular form, oftentimes the rectangular form doesn't represent the polar form completely. It's lacking certain points, and this is part of the reason for that. So we really have to be careful, and the only way to know for sure if your rectangular equation represents the polar equation is to graph both of them and verify. So I'm not going to give you problems where you have to graph them because that's kind of tedious. Even if you use your graphing calculator, you would have to change back and forth from rectangular form to polar form, and the rectangular form is difficult to solve for y, which means you probably would not even be able to enter it into your calculator. You can go online and use the Desmos calculator, and you can try. That'll allow you to do that. So for that reason, generally speaking, we want to avoid this square root x squared plus y squared symbol if we can. So in order to do that, we're going to take both sides of this equation and multiply by r, and it's going to make things a lot easier for us. And then we're going to get r squared here, so we don't have to deal with the square root x squared plus y squared problem. So we get r squared is equal to r sine theta plus r squared times tangent theta. This is going to make it a lot easier for us to change to rectangular form. So r squared is the same thing as x squared plus y squared. Notice that we don't have a square root here now. We don't need that. Now, r times sine theta, that's equal to y. So that makes it really easy for us. And r squared, again, is equal to x squared plus y squared. And notice that tangent theta over here is just y over x. So that makes it really easy also. So that is the rectangular form of this green equation up here. Now again, the only way to know for sure if this equation represents the polar form completely is to graph the blue and the green equations on a calculator and to see if they have the same shape. But even in that case, there might be some points that we can't see that don't really work. So there is some difficulty when it comes to converting from polar form to rectangular form, or vice versa. But generally speaking, you're not really expected to deal with those issues. In fact, most teachers don't even talk about them. So I'm just letting you know that there are some potential problems when you convert. So this is polar form of an equation, and this is rectangular form because down here we have only x's and y's, whereas up here we have r's and thetas. So let's try another one. Okay, so notice it says modifications will be necessary. So this is a special example where we really need to be careful. So we have r, but again we're going to need to multiply both sides by r squared. Again, this is a polar equation because we have r's and thetas. We want to convert to x's and y's. So I'm going to multiply both sides by r again, so we can try our best to avoid square root symbols. So r times r is r squared. Then we have r times cosine theta, and then r. So r squared is x squared plus y squared, as we talked about. That's just the Pythagorean theorem. Now r times cosine theta, if you look at your equations, that's just x. So I'm going to give you one more chance to take a picture of these equations. R times cosine theta is just x. And r, well, that's not r squared, that's just r. So we have to actually square root. And we end up with this equation. But remember, when you square root, this should be a plus or a minus symbol, and that tells us that there may be some problems. And there's actually some very, very big problems. This equation, as you see it here, does not represent this equation up here in green. It fails completely. If you were to graph this equation and then graph this equation, the green equation would give you some sort of a shape, but the blue equation would do nothing. There would be nothing on the window. And that's because this equation just doesn't work. There are very few x and y values that you can plug in to make that equation true. So again, I'm not going to bother you with a lot of these types of problems, but I just want you to be aware that sometimes you can't just convert from one to the other. Oftentimes it doesn't work. But if we can somehow get rid of that root symbol, remember that's the general guideline, is if you can, you want to get rid of this root symbol. So what I'm going to do is I'm going to put this term on the other side. And I'm actually going to show this. You don't have to show this, but I just want you to be absolutely clear on what we're doing here. Usually you don't see teachers demonstrating this, but I just want you to know what we're doing when you look back at this. So I'm adding square root x squared plus y squared to both sides. And I'm going to make that a different color. Sorry, my computer's going a little slow. Okay, so then we have x is equal to the square root of x squared plus y squared plus x squared plus y squared. And now I'm going to take these terms and put them on the other side. Again, you don't have to show the steps here, but I just want you to be aware what's happening. So I'm going to subtract x squared, and I'm going to subtract y squared. From both sides. So now we have the square root of x squared plus y squared is equal to x minus x squared minus y squared. So these all cancel out. So now I can avoid this square root problem, the issue where we need a plus or minus symbol. You never really see the plus or minus symbols written, and that's why we have to do this. So I'm going to square both sides of the equation. And that's going to get rid of that square root. So we have x squared plus y squared is equal to x minus x squared minus y squared squared. So because we got rid of that square root, this blue equation down here does represent the polar equation that we started with in yellow up there completely. So again, if you graph the green equation, you get nothing. The green equation does not represent the yellow equation, but the blue equation does. So I know that's very confusing to think about, but all you have to know is that if you graph the green equation, you get no graph. There's nothing there, because there are very few x and y values that will actually work in that equation. But if you graph the blue equation that does not have a square root, then you get the yellow equation. So the blue and the yellow equations are they're equivalent. So again, this is an issue that is pretty advanced, and that's why most teachers try to just give you equations where there's no real problems there. But generally speaking, try to put all this this confusion and these details aside, and just know that you want to avoid the square root symbol if you can. And ultimately, the way that you have to check to make sure that your new equation represents the original equation completely is to go online and graph both equations. Or you can try to graph both equations on your calculator and maybe take pictures of the first graph and compare to the second graph. So I want you to take a picture of 19 and 20, and a picture, well, you can keep 21 in the window. So you should have these equations right in front of you, and I want you to try number 22, and when you come back, we'll do it together. Alright, we're back. So tangent is y over x, and maybe I should change that to avoid confusion. Tangent squared theta is the same thing as tangent theta squared, right? Now you must use parentheses, because tangent theta squared without parentheses, that does not mean the same thing. So I just want to remind you of that. That's something completely different. That's if you're squaring the angle only. This is if you're squaring the entire function. Okay, so tangent theta is equal to y over x. That's one of our equations. And r times cosine theta is equal to x. So that was pretty easy. We're pretty much done at that point. But we could simplify a little bit by using exponent rule number 4. You can go back to my intermediate algebra course and review exponent rule number 4. Then we're going to multiply both sides of the equation by x squared. And the x squareds cancel out on the left side, and we get x cubed. So this is the simplest form. Let me write that a little better. That's the simplest form of the equation in rectangular version. So you could stop here, but in most textbooks, the answer that you're going to be given is probably something in a simpler form. Now, notice that we didn't have to deal with any square root x squared plus y squared terms. So what that means is we probably don't have to worry about potential problems or loss of coordinates. So if you got that right, good. If you stopped here, that's fine. Okay, so you can take a picture of these two problems, and they'll help you to do number 23. Go ahead and attempt number 23. In this case, in order to avoid problems, you're going to want to multiply both sides by r. Because if you don't, you're going to have to write r is equal to root x squared plus y squared. But remember, r can be negative. So then we'll have to deal with the plus or minus, and mathematicians generally don't want to do that. So if you start by multiplying both sides by r, then you'll get r squared rather than r. And again, many times there are potential problems that occur when we multiply both sides of an equation by a variable, but in this case it's not really going to cause any problems. So try number 23. When you come back, we'll do it together. Okay, we're back. So I'm going to multiply both sides of the equation by r, and we get r squared is equal to negative 3r sine theta. Now if you look at your equations, our tools that we're using today, r squared is equal to x squared plus y squared, and r times sine theta is equal to y. So that expression became y, and r squared became x squared plus y squared. So at that point, we're done. Now, if you wanted to, you could complete the square, and you would find that this is actually going to be a conic. But we don't need to do that. We're just converting from polar form to rectangular form. So again, polar form is when you have when you have thetas and r's. When you have thetas and r's as your variables, that's polar form. When you have x's and y's, that's rectangular form. So why don't you try number 24? Number 24 is going to be more of a challenge. You may end up with a square root x squared plus y squared. So if you do end up with a square root x squared plus y squared, that's okay. But just leave your answer in that form. But if you can, try to get rid of the square root. So try 24. When you come back, we'll do it together. And you want to start by multiplying both sides by r. That's just going to make things a lot easier. You don't have to do it that way, but it's going to be easier. So try number 24. When you come back, we'll do it together. Alright, we're back. So I'm going to rewrite the equation and multiply both sides by r. And we get r squared is equal to 2r minus r times cosine theta. Now the reason that makes things a lot easier is because we know that r squared is just x squared plus y squared, and we don't have to deal with the square root here. Unfortunately, we are going to have to deal with the square root here because we only have r, not r squared. And thankfully this is equal to x. If you look at your equations, that's just x. So at this point, we're actually done. It turns out that this equation does completely represent the polar form, but that's just a coincidence. It would be much better if we could get rid of this square root completely, and you can write this as your answer because it turns out that it does work. But if you wanted to get rid of the square root, we could add x to both sides and then divide both sides by 2. So I just isolated this green square root, and then we could square both sides, and I guess I'll show that just so you can see what's happening. So again, I don't mean to confuse you with all these technicalities, but I'm just letting you know that there are some potential problems that occur when you convert back and forth. So now we're going to square both sides to get rid of the root. So we have x squared plus y squared plus x over 2 squared is equal to x squared plus y squared, and that's probably a safer answer, even though this is an equation that works also. Again, most teachers are not even going to bother with these technicalities, so it's not something you really have to worry about that much. Okay, so we had equations in polar form, meaning we had r's and thetas. And then we converted to the rectangular form, meaning we had x's and y's in the rectangular form. Now, as you can imagine, we're going to go backwards. Now, when you go backwards, you also have potential problems. So I'm going to let you know what some of these problems could be. So if you look at your tools, we know that x is equal to r times cosine theta, and y is equal to r times sine theta. So we have the rectangular form here with x's and y's, and now we're going backwards. We're converting to the polar form. Now we have r's and thetas. Now we can combine those r's to r squared, and at this point you're pretty much you're done. You can actually write this as your answer. There's nothing wrong with writing that, but generally speaking you want to combine anything that you can. But we could go a little further and use a double angle formula. You may remember this formula from my trigonometry course. If we divide both sides of this equation by 2, then we can change the form and use this to help us simplify so that we only have one trigonometric function versus 2. So I'm going to take that equation and divide both sides by 2. And remember, these 2's are not going to cancel out because that 2 is inside the function, so don't do that. So now we have sine 2a over 2 is equal to sine a cosine a, but who cares? What's the point? The point is, this expression here is the same as that expression up there. So we're going to substitute. So we have 3r squared times sine 2 theta over 2 is equal to 1. Then we can take that 2 and put it under 3 just to make things nice and neat. And so there's our equation. Now again, you don't have to get to this form here, but in a textbook you're probably going to see it in either this form or this form. So for your homework, I'm not going to require you to put it in this form. Just be aware of that, this form here. Okay, so it turns out that this equation represents the original equation completely, so we don't have to worry about any potential problems. Not that you really have to worry, but I'm just letting you know when problems occur. So we know that x squared plus y squared is r squared, and we know that x is r times cosine theta. This is the rectangular form with x's and y's, and we converted to the polar form with r's and thetas. Now we can make this a little simpler by dividing both sides by r. Now, generally speaking, you don't want to do that. That causes a lot of problems. But in this case, it's not going to really cause any problems, so we can divide both sides by a variable. Remember, when you do that, you can actually miss a solution to an equation. Well, we're not trying to solve an equation here, so it doesn't really hurt us. So this is now the polar form. And we don't really have any issues when we compare the graph of this equation and the graph of this equation. So this equation represents this this rectangular form completely. But the only way that you could know for sure is if you graph the rectangular form online, because your TI can't really graph that yellow equation because you'd have to isolate y. And so graph the yellow equation and graph the blue equation online and compare the graphs. That's the only way that we can really know for sure if those two equations represent each other. So let's try one more of these before you try one on your own. So here's an example where we're going to have potential problems. So again, this is rectangular form. We have x's and y's. We're going to convert to r's and thetas. So y over x is tangent theta. That's one of our equations. And the square root of x squared plus y squared, well, that's just going to be r. Because remember, x squared plus y squared is equal to r squared. So r is just square root of x squared plus y squared. But r can be plus or minus, positive or negative. Turns out tangent theta can be positive or negative. But in this equation, if x is positive and y is negative, that means this side of the equation is going to be negative. But notice this side can never be negative, because when you plug in a positive and a negative, which is the situation that we're interested in, because a positive divided by a negative or a negative divided by a positive is a negative, then this side is not going to be negative. It can't be negative because there's no plus or minus symbol. I know that this is very confusing, but that's why most teachers don't even talk about this stuff, to be honest with you. But long story short, this equation is something different. It represents something different than this equation. This equation has restrictions, but this equation really does not have restrictions. So this equation is not exactly the same as that equation, because the coordinates that are allowed for this equation are more numerous than the coordinates allowed for this equation. Again, this is something that very difficult to see just by looking at it. And it's so difficult that most teachers don't even pay attention to this stuff. So what do? Well, we'd have to restrict theta. Now, I'm not going to require you to do this, but in this case, theta would have to be between 0 and 90 degrees, or it'd have to be between 180 and 270. Now, how do we know that? Well, one way we can figure that out is by graphing the rectangular form and the polar form and comparing them. But again, I'm not going to expect you to be able to figure this stuff out, because even the textbooks don't really go into problems like that. So just be aware that there are potential problems when converting back and forth. So again, I'm not going to give you any problems where you have to worry about those issues. I just want you to be aware of the issues. So get a picture of numbers 25 and 26 and use number 27 to help you do 28. Try number 28. When you come back, we'll do it together. Alright, we're back. So use your equations, and we know that x is equal to r times cosine theta and y is equal to r times sine theta. Now at that point, you're pretty much done. If you left the form like this, then you're done. But I just want you to know that you can work things around and simplify a little bit. Generally speaking, it's easier to graph polar equations if we solve for r. Again, you don't have to do this. But if you see the answer in a textbook, let's say that you were given this problem in a textbook and you wanted to check the answer in the back of the book, it might show you a different form. So what I'm going to do is divide both sides by sine theta minus cosine theta. And then we have r is equal to 5 over sine theta minus cosine theta. Again, you can just leave your answer in this form up here. If you didn't convert to this form, that's okay. But just be aware that sometimes you'll see that form. So take a picture of numbers 27 and 28. And I want you to try number 29. When you come back, we'll do it together. We're in rectangular form. We have x's and y's. I want you to convert to polar form in r and thetas. Okay, we're back. So r times sine theta is y, and x squared plus y squared is equal to r squared. Now we have to use exponent rule number 5, which tells us when you raise a power to another power, you just multiply the exponents. Now, you could leave the answer like this, but it's very unorthodox to leave something in this form when you can convert it to this form. And you could leave your answer in this form, but in this case, no potential problems are going to result from dividing both sides by r in simplifying the equation. So we can divide both sides by r, and we get sine theta is equal to r cubed. Now, if you didn't get all the way down to this form, that's okay. The most important thing is that you know how to convert to r's and thetas. Now again, if we wanted to confirm that this equation represents the rectangular form completely, we'd have to graph the yellow equation and the green equation and compare them, compare the graphs. But again, I'm not going to make you do that. Okay, so try number 30. The purple Pythagorean identity might help you. When you come back, we'll do it together. Alright, we're back. So x is r times cosine theta. That's one of the equations that you were given. X squared plus y squared is r squared. Y over x is tangent theta. That's another equation you were given. And notice that some of these r's cancel out, which makes it easier for us. So we have cosine theta over r. And I'm going to change this exponential form because it's usually written like so. So then we have cosine theta over r is equal to, and this is where we're going to use the Pythagorean identity just to simplify things as much as we can. So once you change to this form, we're in the polar form. So you don't necessarily have to keep simplifying, but if you can simplify, generally you want to do that. So now we can actually simplify even more. I know it's kind of annoying to have to keep going. And again, you don't have to simplify, but it's important for you to get used to seeing how to simplify these expressions. So we're going to multiply both sides by r, and that's going to get rid of the fraction. Then remember, secant squared is 1 over cosine squared. We learned that in my trigonometry course. So then I'm going to multiply both sides of the equation. by cosine squared. So I'm now multiplying. And we get r is equal to cosine cubed theta. So again, don't be distraught if you didn't get to this form down here. The most important thing is that you know how to change from x's and y's to r's and thetas. And it turns out we don't have any potential problems when comparing the blue graph, or the graph of the blue equation, and the graph of the yellow equation. So the blue equation represents the yellow equation completely. So have you got that? Good job. That was the class today. If you'd like to take screenshots of all the work that we did to help you with your homework or to study for tests, go ahead and do that now. Here's screenshot number 1 and number 2 and number 3 and 4, 5, 6, 7, 8, 9, 10, and don't go before you get the homework. Here's the homework assignment. Remember, the homework is not optional. Here's screenshot number 1 and screenshot number 2 and number 3 and number 4. And remember, it's not enough just to attempt the homework, it must be done correctly. So here's the answers and the remaining answers. Get that homework done completely, correctly, neatly, and keep it in order in your binder. And I'll look forward to seeing you in the next class.